Hey everyone. So we're going to kick off this very long, potentially live stream uh, on the hour, so like in 20 minutes or so. So the way that this is going to work is if you have any questions, just put them into the chat. Hopefully everything will work. I adjusted some settings, and clearly if you adjust a lot of settings for making a stream better, they clearly will all work in unison and everything works perfectly. Yeah, so I'm going to be covering everything on regular languages today. So this is going to be, I should put here. So this is going to be one of four. So there are going to be, that last parenthesis was not big. Yeah, so there are going to be 4 sessions. This is going to be the first one. If you have any questions, put them in the chat. Will this stream be saved? Yep. So it's going to be saved. You don't have to watch all of it, or really any of it. I hope you watch all of it, but yeah, so this stream will be saved. If you have any problems that you want me to go over, or any question that you have, like you don't understand something, just put in the chat. I'm constantly watching it. Hopefully all the stream settings work. If it doesn't, then I will have to stop the stream and then restart it and maybe adjust the settings. But hopefully I won't have any like drop frames or anything. I put it on low latency because I want this to be more interactive, but I didn't put it on ultra low latency because I didn't want the video quality to drastically fall apart. Just asking because I have class in a few, but I really watch the entire thing later. Yeah, so the whole thing's gonna be saved. It may take a while for YouTube to process it, but it will all be available. And I will have a playlist once we do all these 4 sessions, where it'll just be the entire course in however many hours, I'm not sure. So Manas, can you do pumping lemma? I will do the regular one because today is about regular languages. So I will cover that. Yep. Not context free though, because it's not regular. But the pumping lemma for CFLs is coming in a normal video within the next few weeks. I think next week it'll come out. I'm just getting started with CS. Thank you for joining Anirudh. Sorry if I pronounced that wrong. I already studied that basic math. What should I start if I want to study theoretical stuff? This class. This class. Yeah, so this class is pretty much the jumping off point if you want to study theory, other than algorithms, I guess. So I have snacks here, and I might cough because I've been having almonds this morning. Yeah, so this class and algorithms are pretty much the only jumping off points, and this one I argue is better, but yeah. All right, so we'll start right on the hour, and if any of you are confused by anything that I say, which is totally possible, just ping me in the chat. I'm watching the whole thing. Oops, accidentally let that go to sleep. Yeah, so cool. And feel free to recommend this live stream to any of your friends who are studying this class and want to need help for studying for their final exam, which is coming up in a few weeks. So I have all of these 4 coming out within the next few weeks. So this one is obviously today. Context free is this coming Sunday. Then decidability stuff, the 3rd one, is the next Sunday, and undecidability is the following Sunday. So it's today, Sunday, the next Sunday, and then the next Sunday. Let me actually look that up. So let's see. So we have, let's just make sure that that's right. Okay. Never mind. Oh no, I fixed that. Never mind. So regular languages is going to be today and today. Oh God, what is today? Today is the 11th. So that's 11 November. Then we're going to have one on context-free languages, which is going to be on, let's see if I get my date straight. It's going to be the 15th of November. Then we'll have one on Turing machines as well as decidability. On, what is it, the 22nd of November. And then finally, we will have one on undecidability, because that's all the course goes up to, which will be on the 29th of November. Yeah, it is the 29th of November. Okay. So for like the next 15 minutes or so, let's you can ask me any questions or whatnot before we undertake a potentially long live stream. And one thing that we might do, because I don't want to be sitting in a chair all day, and you probably don't either, is when I go through a series of concepts, once I'm done with one, I may take a few minute break to stretch or whatever. But we'll worry about that when we get there. I just thought of something interesting. It might be fun to do like a speed run of teaching a certain concept, like the pumping lemma. I have like a really short video, like 4 minutes or something, and one for Rice's theorem. It might be fun to like do a whole subject like this and do a speed run, see how fast you can convey all the concepts in a clear and coherent way. Might be fun. All right, so let's see. I'm pulling up analytics just to see how things are going. All right, so we got that, and no drop frames yet, which is great. So Panos and Ashish asked pretty much the same question. Yep, it's going to be all saved completely. Yep, unless YouTube screws up, but I'm doubtful of that. Yeah, it should all be saved. It may take a while to render, but it will all be saved. Yep. So the funny thing is that this will be the 5th time I've taught the class, because I've taught it in a university basically 4 times now, and I'm going to be going through the whole thing in 4 increments, and so I'm covering the whole class, which is pretty cool. You are welcome, Ashish. Any questions that you all have? Yeah, thankfully there's no drop frames yet. That's awesome. Okay, let's see. So I'm gonna organize all the notes that I have. Oops, I opened them up in the wrong way. All right. Yeah, I want to make sure that I am crystal clear in the examples that I do, because I usually I don't usually teach like a whole quarter of a class all at once. So this will be an interesting experiment. But what questions do you guys all have? And I may ask questions about the material at some point, and you can just feel free to answer in the chat. It's sad that like I don't have a set of students in front of me to ask them questions and get the answer right away, but is L2 minus L1 recursive enumerable where, okay, so that's not related to regular languages. Okay, so only ask questions about regular languages, but the answer to your question is yes. Oh, yeah, it is. I had it in the wrong order, but yeah, it is. But only regular languages today. Let's adjust the camera. Make myself look as professorial as possible. Can I explain this? Not today. If you ask during the decidability stuff, then yes, I could. But a hint is closure properties. Use closure properties. How can I make the best of my college experience? I'm going to be starting this year. If you're going to be starting college and with this class, that's pretty impressive. But yeah, it's mainly to try to form connections with people as a CS major. Yeah, to converse with with your fellow students and your faculty as much as possible, given the current situation, of course. But yeah, to try to form personal connections with other people and not just be another number in the crowd. And by number, I mean your ID number for when you are taking classes and whatnot. I didn't do that. I was purely an academic person. Well, I happened to relatively succeed, but it's just, it's not for everyone. So try to form collaborations with people if possible. Rahul said, would you teach how to make finite automata for various languages too? Yeah, that's what today is all about. Yep. All about finite automata. Okay. Tell me that. Got like 30 friggin' windows on my screen. Gotta manage them all. Jeez. What am I doing? Okay, yeah. What other questions do you have? Can't do that. Yes, let's move. And we just hit 110,000 views, which is awesome. Thank you all for watching. And after today might bring in a whole bunch of views, which is really cool. But I'm focused on you all learning as much as possible. I'm not totally focused on the number of views, but obviously more views are better than fewer. It's just getting it's getting people to bringing them into the easy theory family, so to speak. But yeah. No, thank you for saving my butt in this computing course. You are welcome. Okay, so I'm looking at my stream in one location, and I'm seeing a lot of drop frames. Can you, can someone tell me whether you can actually see it? Whether the stream is okay? So how long will today's session be? I have no idea how long it's going to be. I might regret this. It drops occasionally. Okay, I do see that. Is there a way that I can fix that on the fly? Okay, so it is dropping. Okay. Let me try to fix that. So I'm gonna end the stream and then retry to start it. Because I don't think there's a way that I can change the I can't change the stream quality on the fly, which is kind of annoying. Okay, so I'm gonna try to end the stream, and I'll just restart it with. Okay, I adjusted some settings, lowered the frames per second, so hopefully this will be better. Yeah, I'll need 60 frames, and I lowered the quality. So, sorry about that. Hopefully it should be all good now. Good thing is I can stop and restart the stream whenever I want, which is pretty cool. So let's see. Let me put you in here. Doubt WXW reverse Y. Okay, so that one is regular. That's a trick question. I think I've covered that on the channel before. I think it was a gate question that I've done before. So can someone tell me whether or not this is dropping for you? Because okay, so I'm getting quite a few drops. It's like at random intervals. Internet quality here sucks. Okay, it's okay. Brother. And I don't have enough space to store it. I don't have an external hard drive. God, why is it dropping so much? It says my stream quality is good. Jesus, of course. Let's see. Here, let me. Hopefully that'll fix things. I lowered the quality even more. It's just annoying. I doubt that that really has anything to do with it. I tried to lower the quality. I'd rather not, but okay. So I'll try to just go with this. Hopefully all the audio comes through, but all right. So welcome everyone to this probably marathon stream. We're going to be talking about theory of computation stuff, and we're going to be talking only about regular languages. Okay, I need to fix something about chat. Okay, so that's good. Okay, so we're going to be talking about the first part of this course. So the idea of the theory of computation is we want to be able to understand, we want to understand what computers can do. So are there certain problems that computers can do that can't be done with a less powerful computer? Or are there some problems that can't be done by any computer, regardless of how powerful it is? So you could actually show that there are in fact unsolvable problems, whatever unsolvable means. And the reason is that from what we're going to learn about, unsolvable, there are only countably many possible algorithms that could ever solve a problem, and each one of those only solves one problem, but there are uncountably many possible problems. And since every single algorithm only solves one problem, therefore there must be a very large number of problems that don't have any algorithm to solve them. So that shows that there are some unsolvable problems. I want you to think about how do you actually prove this, but I'm not going to do that here. So the question is, well, can we actually find an unsolvable problem? That's the whole point of the entire class. But even if we have a problem that is solvable, are there such problems where if we restrict the computer in some way, like we don't give it an add instruction or something, then it can't solve those problems? So like if we make the computer less powerful, can we restrict the number of problems it could actually solve versus a full powered computer that we use where it could solve it? So it's just finding what is the hierarchy of what problems can be solved or not. So if we think about this, well, if we really want to understand that, we need to understand what a computer is to start with. And we need to have some kind of formal notion of what computing something is. So what, in fact, is a computer? In fact, all of these words can have quotation marks. Oh, not what is a computable. What is a computer? I'm going off the rails already. All right, so what is a computer? If you actually really think about it, a computer is just a device that converts inputs to outputs. So let's say we have our computer of some kind right here, and I'm going to represent it by this yellow square, not square, rectangle. And it could have a bunch of inputs. So like maybe there's one here, there's one here, there's one here. There could be a whole bunch of these. It doesn't have to be just one, but we'll find a way to restrict that without loss of generality. And on the other side, actually what I'm going to do is I'm going to utilize colors. So let's change these to, I don't know, red. And on the other side, let's keep it orange. So then on the other side, we have a bunch of outputs. So we have an output here, we have a bunch of outputs, and let's say there's one here. Okay. And of course, as always, please leave questions about any of this into the chat. I have it open down here so I can see. All right, so we have inputs here and outputs. And what the computer does is it looks at all these inputs, does stuff, and it produces outputs. And it doesn't have to be the same number of inputs, outputs. It could just be one of both, or one of either, or not. But what we can do is we can restrict the number of inputs to be 1. And why is that the case? What we can do is let's say we have 3 inputs, and this can generalize to any number. So let's say we have some bit sequence for input 1. We have one for input 2, and I'm going to make it different on purpose. And let's say we have input 3 here. Input 3 and 0, 0, 0. I'm just making this up. Okay, so how do we actually restrict the number of inputs to be 1? Well, what we can do is we could do something which is called multiplexing. We're not going to actually use this term later, so it's, I guess, kind of useless. But we're going to use something called multiplexing. Is an epsilon a case of no input? That is a great question. The thing is, what we can do is we could cut off each one of these at a specified point and then switch to handling the other inputs. So like when one of the inputs is done, we can focus on the other ones. And you'll see that in a sec. Good question though. So multiplexing, what it is we look at the first bits of all the inputs. So let's say look at this one. And what I'm going to do is I'm going to put it down here. I'm just going to paste it down. Then what I'm going to do, let's use pink for this. I'm going to take the first bit of the next one and I'm going to put it in the next position. Actually, what I'm going to do is I'm going to change these to the appropriate color. All right, I can't change it. All right. So, okay, yeah, I won't circle it, I guess. So, yeah, so this one right here is going to be for orange, second input, and then we need one for the third one. And then once we're done with those, since those are all the inputs, we focus on the next bit of the first input, which is 1 in this case. And we will take the second bit of the second one, go next. And then the third one down here. And then we just carry on like this. So, and based on Rahul's question, if one of these drops out, we can make a note of that and just say, oh, now we're only working on input 1 and 2 this time, if 3 dropped out early. So if we see this sequence, what we can do is we can extract what the original inputs were. For the first one, it's just the first, the fourth, the second, seventh, etc., all the way through. And then for the second input, it'll be second, the fifth, the eighth, etc., and the same thing for the third. And of course, this generalizes to any number of inputs that we want. So in fact, we can restrict the number of inputs to be 1, which is pretty cool. So we can revise our model right here to get rid of all these unnecessary, obviously, inputs. That was sarcasm. Of course, we want real inputs in real life, but we could, without loss of generality, have a single input here. But we can also use the exact same idea for the outputs. We can multiplex the outputs and get all of the individual bits into one bit sequence. So in fact, we could restrict the number of outputs to be 1 also. So I can get rid of all these unnecessary, obviously, outputs too, which is pretty nice. So we have a single output this time. But we can actually go even further. What we can do is we can basically, for the most part, so it reduces to 1. Thanks, Tom. So here we can actually almost eliminate the output entirely. What we can do is we can have this instead do one of two things. It can either output a 1 or a 0. So a single bit versus versus a whole string of output. And the reason for that is, if the output is possible to be created from some input, we'll mark that as a 1. So whenever that input comes in, assuming the computer's deterministic, which we can assume it is, then we'll produce a 1 in that case. We'll be able to input the logic in. if it produced this particular output, then we'll produce a 1. And if this this input does not correspond to any possible output that we desire, then we will put a 0. Or if we have a string that could be outputted that does not correspond to any input, we'll have it correspond to a 0. It's not non-deterministic, but it's along those lines. So what we can do is we can assume that there's one input and a single bit output. Okay, so let's actually write that down. So we can assume that there's a single input, and 2, we can assume that and then we can assume that there's 1 bit of output. I can't do both the inputs and outputs to be single bits, because that would only have 2 possible inputs. But I can do it with the outputs. Okay, so what can we actually do here? So if you think about it, what your computer does in the computation part is, within this part right here, which is obviously the more interesting stuff, is if we think about what happens, is we have like our CPU, and an instruction is coming into the CPU, and what's going to happen is a whole host of possibilities after this one instruction happens. So like the memory contents can change, or something gets written. I don't know necessarily what happens. But what happens is the quote-unquote state of the system, of the computer, changes possibly. It could be exactly the same after, which is, I guess, unlikely, but we can think about the machine being in a certain state, which is the contents of the registers, the memory, what's written on the hard disk or solid state or whatever, but it's a certain state of the system at a given moment. And then when we process an instruction, then the state will be updated. It may be exactly the same, or it could be different. So what we can think about is a program is just a bunch of possible states, and when you read an instruction, you go from one state to another. So then what we can do is we can try to think about, well, if we have all these states, how do we actually model the journey from one state to another? So that's what this whole class is about. But there's several assumptions that we're going to make here. All right, so some assumptions that we'll make are, I'm going to label them A, B, C. So A is going to be that we have a fixed internal memory. And B, what we have is that once we are done reading the input, then we are completely finished. So once done reading the input, the machine stops. Okay, let me move that down. So the reason for this assumption for A is that if we allowed the memory to grow as much as you want, then that actually changes the model of computation. So I'm focused on this one. So this is really needed for talking about the things we'll talk about. And the reason for the second one is we want to, if you think about what the input is, you could, without loss of generality, assume that the input is read from left to right and never backtracks. So it always moves forward, it doesn't ever move back. So this one we can assume without loss of generality. This one changes the model of computation, but it makes things a lot easier. We want to make the model as simple and easy to understand as possible. Okay, so, but also what we have is when this input occurs, well, we got to start the machine somewhere in some state, because the machine's in a certain state. We need to be able to start it in a state somewhere. So let's talk about yeah, okay, so let's put that as an assumption too. So machine starts in some state. Okay. I don't see how many people are watching. I just want to see what's happening. Actually, I'm having really low drop frames. That's great. Awesome. I'm just taking a short break to see how many people are watching. Okay, awesome. So we got a handful of people. Awesome. Okay, so let's look at a particular example. So here's an example. Yeah, so an example machine of this type. So here's how this is going to work. So I'm going to have 2 states. So it's a very small machine. If you think about your memory, the total number of possible memory contents is ginormous. But we're only going to have 2 states here. So it's a very simple machine. So I'm going to make the machine, and I'm going to discuss after it what it does. So we have these arrows, and I have a state called Q1 here. So let me tell you what this machine's all about, what all of these symbols mean. So yeah, the video's better. So I guess it really is the because the only thing I changed was the quality of the video, so to speak, that's uploaded. So maybe that's the reason. Okay. So these 2 things right here, the things in circles, are states. And the Q0 thing and the Q1 thing, those are the state names. Yeah, Rahul jumped the gun. But yeah, so those are state names. So what we have for the double circle, so double circle, are is a 1 state. So remember that the machine will output a 1 or a 0 depending on what the input is. So the states that have a double circle, I'm designating those as a 1 state. And any state that doesn't have a double circle, those are the 0 states. So it's a binary classification of what states are which. Okay, so you may be thinking, okay, what are these things right here? These are what are called transitions. And what these are if we're in a certain state, let's say Q0 here, and I see a input 0 given to me, then I will follow the transition that is labeled 0 and visit the state at the head. Is it the head? Yeah, it's the head of the transition, which is where this transition is pointing to, which is Q1. So if we read, one more thing. So this arrow coming from nowhere is something that we're going to call the start state. And we're going to assume there's only one of these. Okay, because the machine's got to start somewhere, and if it could start in any one of multiple places, then we don't know necessarily where to start because the machine has to be deterministic. Okay, so that's the start state. So Q0, that's the name of the state. I have no idea why they call them Q. I know the original paper for these called them Q, but I would think S0 would make more sense for state. I have no idea why. Okay, so we have this machine right here. So it's got two states. Q1's the only final state. We got two transitions in between, and Q0 is the start state. Okay, so what are we going to do here? Well, what we're going to do is, if we read the input, let's just say, for example, so example input, let's say is 0, 0, 0, and nothing else. Then what will happen is we got to start in the start state. So we're in Q0 right now. We will read the characters one at a time. So the input's being processed this way, from left to right. Although for this string it doesn't matter. So we're reading the 0, and then once we read the 0, we're done with it. So once we read this 0 coming over here, then this 0 gets chopped off, and then because we're done with reading it and we'll never see it again because we can never backtrack, then we have another input, which is 0. So we're in Q1 right now, reading a 0, going to Q0. And so because we're not done reading the input, we still have more input to read, and I cut that 0 off. And then once I am in Q0, I read another 0 to go over to here. So that is the final third 0. And because there's no input left anymore, we are done. And because this string of characters ended up in Q1, which is the 1 state, that tells us that we should give a 1 as the output. So this is a 1 state. If we had example input 0, 0 and nothing else, then you can see that if we start in Q0, go to Q1, and then back, then we're not going to output a 1, we're going to output a 0, because Q0 is not a 1 state. Okay, and Rahul said, is it necessary to have at least 1 state? Yes, because I have to have a start state, because the machine has to start. But it could be that the machine only has 1 state, but it has to be at least 1. Good. So we could make this more complicated if we wanted to. So let's do another example. So example 2. This one's going to have 4 states in it. So Q0 is again the start state. Usually the state that's called Q0 is the start state, but it never has to be. So this one has 0s coming back and forth, 1s coming up and down on both sides, and 0s going across. And the final states in this, the 1 states in this case, I'm going to put in red, are going to be Q1 and 2. So those are the only 2 1 states. So we could analyze this right here, but note that every single state has a 0 and a 1 coming out of it. So Q0 has a 0 leaving it, also has a 1 leaving it coming down here. And the same is true of Q1, 1, 0. Q2 has a 0 and a 1. Q3 has a 0 and a 1. Okay, so you could analyze this, and I want you to actually think about what this machine does. And the thing to keep in mind is that every state, or this is something that we would want. Every state has an outgoing transition for all possible inputs. Okay, for all possible inputs. And the reason you would want such a thing is you want the machine to be completely deterministic. So if you're in some state and you see a 2, for example, and you wouldn't know what to do because there's no transition telling you what to do. Okay, so this is not a logical consequence. This is something we want, and we're defining the machines that we have here to have this property. Okay, so every state has an outgoing transition. It doesn't have to have any incoming ones. That's totally okay. It could have a state that's just not possible to happen. Maybe like your real computer having all zeros in its memory. That's very unlikely to happen. So, or even impossible. So, yeah, so some state just may not be possible to reach. So, in this case, for example, yeah, can the machines for different problems be the same? No, but we could have different machines for the same problem. So, in fact, if you think about it, what does this machine do? So, if you're in this state, either Q0 or Q3, no matter what you do, you will be in one of the two states here that are in red. And if you're in either one of the red states, you're gonna whatever you read next, you're gonna be in one of the non-red states. So you can actually see this and say, well, isn't that just like the length of the input being even or odd? Because no matter what you do, you're gonna alternate between being a 1 state or a 0 state. And it's an alternation here. So we can actually simplify this big boy to be this thing. So I'm going to have 2 states. I'm going to call even and odd. Can't imagine why I'm calling them those. And then I'm going to have 2 inputs on this transition. So this notation here is 2 transitions. So whenever I say something comma something on a transition, that just means 2 different transitions. And also I should say final state. So the final state should be this one. So odd, or the 1 state, I should say. I would actually urge you to actually think about why these 2 machines do exactly the same thing. So they're very obviously different machines because they have a different number of states, but they in fact do the same thing. But the machines for different problems can't be the same because each machine only solves one thing because it's completely deterministic. Okay. Yeah, so this one, in fact, is minimal, and this one obviously isn't because I claim they have the same functionality. This one has 4 states, this one has 2. Okay, so, of course, oh yeah, so there's several things I want to tell you about. So, if we look at, say, the input 0 just by itself, then if we start in either the even or the 0 state, we're going to end up either in Q1 or the odd state, which is the 1 state where we output a 1. So I'm going to call that behavior accepting. So the machine accepts that string because it ends up in a 1 state. Oh, and we can actually call these accepting states instead of 1 state because it's, yeah. Oh, it dropped? Huh. I don't see any more drop frames, but okay. Maybe it did for you. Apologies for that. If we look at 1, the input just of 1, then that accepts 2. But there's a very special type of input, which is called the empty string, which we're going to denote by epsilon. If you use lambda, that's fine. I use epsilon. Okay? In fact, I've seen people use capital lambda, which is weird, but this one is not accepted. Why? Because this input right here, so I should take a note here. So this thing is the empty string. Okay. Yeah, so this is the empty string. So this is the only string with no characters in it at all. So if we look at what the machines do, no characters means you don't execute any transition at all, because each of the transitions reads a character, but if you have the input with no characters at all, then you can't take inputs. It can't take a transition. So in both, no matter what happens, you're stuck in the start state, and that's where you stop. And in both cases, it's not an accept state, because this is not an accept state, not an accept state. So epsilon is not accepted. Yeah. So like if you program, it's where you have double quotes with nothing in it, or single quotes if you use Python or something, with nothing in it. That's exactly the same idea. Okay. So, but we can talk about these pretty pictures all day long, but this is a theory class. We want to be able to talk about these things formally. So these objects have really nice names. So it's called a deterministic, which is exactly what we want, deterministic finite automaton. And we're going to denote that by DFA. Has the following attributes. Or I guess exactly the following attributes. So it has 5 pieces. So 1, 2, 3, 4, 5. And those pieces are going to be, yeah, set theory coming, yep. So it has 5 pieces. It's going to be Q, sigma, Q0, F, and delta. This is different than how I usually order it for a reason we'll see. So the Q here, not a conspiracy theory, Q here is a finite set of states. Okay, so it's just a set of states. It's any finite set that you want. And the reason we want it to be finite is if you allow it to be infinite, then that actually changes the model of computation. So we really want it to be finite. And the size of our computers is finite, so the total number of states is finite, so it makes sense for us. Is epsilon or empty string same or different? They are the same. Epsilon is just the Greek name for epsilon. Yeah, QAnon, obviously. This is how QAnon's getting out, obviously. Anyway, so the finite here is corresponding to the word finite here. The automaton word is just a fancy word for Turing machine. It dropped when you said not a conspiracy theory. Yeah, no machine can have infinite memory, that at least in our physical universe. We could talk about the theory behind it, but it can't physically exist, as far as we know. Okay, so as a finite set of states, sigma here is a finite, for the same reasons, input alphabet. So it's just telling you what are the possible inputs that you could possibly get. Okay, so in the example we did before, it was 0 and 1. But I can make that A, B, C, or the letters of the English alphabet, or whatever you want it to be. It's just a finite set. Q0, and you saw that before, so that's going to be some element of Q. So that tells us that we must have one state. And what is this thing? This is the start state. And by the way, when I say state, alphabet, and start state, those are just names. So that's not really a formal thing. The formal thing is saying finite set, finite, so this is a set 2. This is an element of a finite set. That's the formal part. The F here stands for final states, which is the same thing as except states, and is just some subset of Q, of the set of states. It could be all of the states, in which case every state is an except state or a final state. It could be that no states at all are in this set F. But all that matters is that it's just some subset of Q. Okay, I see your question, Rahul. I'll get to it in a bit. So this is set of final states. The important thing to note, and we're going to get this later, is that the final states are a set of states. Okay, it's not a state or a bunch of states. It's a set of states. Notably, if it's an empty set, then, which means it has nothing in it, then it's still a set. It's not like the empty string, which is a string of characters, which just happens to have nothing in it. What is delta right here? This is the transition function, and we're going to talk a little bit more about what this is. So what is this? This is the mechanism for going from one state to another one. So remember, in order to go from one state to another one, you have to be in a certain state, figure out where you are, and a certain input that you read, and you go to a certain state once you know those two things. Once you know the state that you're in right now and what input to read, then you know where to zoom off to. Okay, so how do I actually denote this as a function? So note that we needed to know what state we were in and the input character. So that tells us we need some state of Q and then cross sigma, because we need an input character. I'll actually denote this. So we got to know the state we are in. We got to know what to read. And once we know that, then we know what state to zoom off to. So the output of this function is just a single state of where to actually go to. It's not technically a directed graph because there's a label on states for and also the transitions. So you can think of it as like an edge labeled graph in some sense, and with a start state, so like a given state, but it is a directed type of graph, but it's not quite right. Okay, so there's one more thing I want to say about this transition function, which is that no matter which state and input symbol that you provide, you should be able to figure out where to go. So no matter what state and what input you provide, you should know what to do. So this function is what is called a total function. Okay, so a total function, all it means is that actually I'll write that. This means every possible state input pair is defined. So it doesn't have anything to do with like bijectivity or injectiveness or surjective, if you happen to know what those are. So it might not be possible to reach some state somewhere. So it's not saying that we hit every state, but it's that, or that even if we have two input pairs, that they have to map to different states. They could map to the same state. As an example, if we look up here, this transition labeled 0 goes to Q1, and this transition from 3 on 1, they go to the same state. So they map to the same place. Yeah, so it is a mapping and it is a total function. So total function means every possible state input pair is defined somewhere. Okay, so let's do a formal example. So I'm going to take this big boy downstairs, see if I can do it without any issues. Paste. So this is obviously a pretty picture, but I want to define this formally. So define formally. So how do we do that? Well, we need to define the 5 pieces. So Q, sigma, Q0, F, and the transition function. So remember that Q is a set of states. So there are only 4 states in this thing. So I gotta be able, I'll erase these columns because I don't need them. So I'm gonna have Q, of course, be a set of states. So I have to write a set because it's a set of states. And I'm gonna put all 4 state names in because that's what the set of states is. Now, the input alphabet is just all of the things on the transitions. So we got to make sure that it's a valid DFA. Well, if the input alphabet included anything other than a 0 or a 1, then this thing cannot possibly be a DFA because there's no transition labeled whatever the other character is, like 2 or A or whatever. So the input alphabet, in order for this thing to be a DFA, it has to be 0 and 1, which are the characters on the transitions. Okay. Q0, what is the start state? Well, it's called Q0. So I just call equal Q0, which is easy. What about the final states? So remember, the final states are a set of states. It's not just a state, it's a set of states. So just like before, I need to write a set down. And what are the states in this set? Well, it's the ones that have red circles in them, or I guess around them. So it'll be, in this case, Q1 and Q2, and no other state. Now we get to the transition function. So we better be able to specify formally which state you're in and what input to read and where you actually go as a result of those 2 things. So how do you actually do that? Well, the easiest way, and the one that I recommend you do, is something called a transition table. It's just really compact. So the way that you do this is you make a little table like this. Yeah, make sure that fits on the screen. So the columns are going to be the input symbols, so like this, so 0 and 1. And the rows are going to be each of the states. So Q0, Q1, Q2, Q3. Make sure it fits. So then I'm going to put some dotted lines in between so we can see what's going on. Can the final state set be empty? Yes, it can. Yep. That's totally possible, in which case the machine does not accept anything. Yeah. So what we are going to put into these entries is if we look at that row, so let's look at this cell. So we look at the row that it's in, which is Q0 row, and what input symbol, which is the column that it's in, and figure out where we actually went before. So this one says Q0 on 0 goes to Q1, and so that goes to Q1, so I'm going to put Q1 here. Q0 on 1, where does that go? That goes down to Q2 down here. So I put Q2 in here. Q1 on 0, that's going to go to Q0. and correct me if I make a mistake. I'm prone to make mistakes on this. Q1 on 1, so the 1's going to go up and down between the rows of the DFA. So we're going to go to Q3 in this case. Q2 on 0, where does it go? It goes to Q3. Q2 on 1 goes to Q0. Q3 on 0 goes to Q2. Q3 on 1 goes to Q1. So being a total function, all that means is that the transition table has every entry filled with some state. That's another way to think about it. Okay, so what I'm going to do is I'm going to take a break for like 10 minutes or so, and then we'll be right back. So I'll see you all then. All right, so let's get back into the swing of things. I don't know if anything's been... Yo. Hi, hello there. All right, so we were talking about these DFA things. So let's introduce some definitions. So, yeah, so so here are definitions. So the computation of a DFA M on W, I'm using notation that I haven't talked about yet, on input W is the sequence of states visited. So like in the case of this one up here, if we look at 0, 1, 0 as an example, the states that you visit are Q0 at the beginning, then 0 going to Q1, so Q1's included, then 1, Q3, and then 0 to Q2. So in this sequence, because it's a sequence and not a set, states can repeat here. So repeats, states are possible. So like in that 4-state example, we can go around many times. All right, why am I getting notifications? That's not good. Yeah, but you can repeat states. Okay, so that's that. Then, yeah, okay. So a computation is accepting. So I'm going to use a different color for this. So accepting, it's happy greens, accepting. If the last state in that sequence is in F. So we have this sequence of states, and if the very last one is a final state, then we will say that the whole computation is accepting. And I know this is definition hell, but a language is a set of strings. And crucially, note that this set here can be finite or infinite. It could be either. And then one more, I think, yeah. So then this is probably the more important one. A language, which is a set of strings, is regular if it is the language of some DFA. If some DFA has that language, and by has that language, that means this is the set of strings that have an accepting computation. Accepting computation. Okay, so let's just do an example. So let's do the really simple even odd example. So even odd. And let's just do 0 and 1 back and forth between them. Then with the language here, the language of this DFA is the set of all strings that have odd length. So in English, what this means is all strings over the alphabet sigma being 0 and 1. God, that was an awful sigma and an awful 1. So sigma and 1. having odd length. Okay, so that's the language that this this DFA accepts, and it's pretty easy to see why that's the case. But so then, therefore, we can say that L in this case is regular, because here is an example of a DFA which happens to have this language. Okay. I think I just found an understanding to why the pumping lemma works. Okay, we haven't talked about pumping lemma yet. But yeah, one thing to note is that the number of computations is always 1 in a DFA, because the entire machine's deterministic, so you always will be able to execute a transition. So you will always have exactly one thing to do at every single point, which means you have 1 total computation. The computation may or may not exist, accepting may or may not exist. So if you don't end in a final state, then you don't have an accepting computation. So the number of computations is 1 always, but the number of accepting computations could be 0 or 1. It can't be more than 1 because the total number is 1. Okay, so let's just talk about some examples of this, some more examples. So one thing that we haven't talked about yet is something called sigma star. So this is the set of all strings over sigma. By over sigma, I mean that means the characters in the strings have to belong to this alphabet right here, or whatever this is. And I claim that this thing is regular. Yeah, so why is it regular? Well, all I need to do is to produce a DFA for you. So if I say I'm going to have a Q0 state that's accepting and will self-loop on all characters in sigma, then that accepts everything, because every single transition is just going to loop back to Q0. A state can go to itself like this, and that will accept every possible string, even the empty string, which just parks itself in Q0 and doesn't take a transition. On the opposite end of the spectrum, we have the empty set. So this is the empty set. And I claim that this one's regular too, because I can do the exact same idea, but I have no states being final, meaning Q0 is the only final state. So again, all characters in sigma go here. Okay. But there are many other languages that you could consider. For example, if you have, say, sigma star, which is all strings, but you take away the set which just has the empty string in it. So in English, what this means is all non-empty strings. So every string that is not empty, okay, because we only take away the empty one. So then it turns out what you can do is something like this. We can't get away with 1 state, but I can get away with 2, which is, so this will be all chars in sigma, whatever it is, going to a state Q1, and that has a self-loop on all chars. Because the only string that will get stuck in here is the empty string. Any non-empty string must take this transition, which will go to a final state. And so that proves that this is regular because we have a DFA for it. And you can check that it's a DFA too. Okay. So the thing to note here is that languages are sets. So if we want to do something interesting, we want to look at some set operations because languages are in fact sets. So let's look at some set operations. Well, we could union two sets together, or we could take their intersection, or maybe the complement with respect to some universe or something. So we are going to talk about set operations on regular, not necessarily regular, but it could be any language, any set of strings. So one thing that you can do is we can union, intersection, or complement, or whatever. But there are other things you can do because these are sets of strings. So what you can do is you can take one string out of one and concatenate it with a string from the other one. So that's called concatenation, gluing two strings together. Okay. Maybe we want to be able to pick a string out of a language over and over and over and then just glue them all together, like repeated concatenation. We can do something like that too. So we're going to say that let's let C be a set of languages. So it's a set of languages. It's just a bunch of languages. Then we say that C is, and the term here is closed, under operation, and I'm going to denote the operation, this is called O plus, because it's O around a plus symbol. So it's just the name of an operation. This could be union, intersection, or whatever. We say that it's closed under this operation if applying that operation to languages in that set C results in a language that is in C. And you're thinking, what in the hell is that? So it's kind of like if you have the integers and you add two integers together, then you're going to get another one. So we can say the integers are closed under addition or multiplication, but they're not closed under division, as an example. Like 1 divided by 2 is not an integer. So integers are closed under addition, multiplication, subtraction, but not division. And we're using the same idea, but for languages. So there's several operations that I want to tell you about, which are called the regular operations. And note, the regular here doesn't have anything to do with regular language, because these are just operations that can work on any language at all. So the operations are a union, which is pretty clear what it does, concatenation, and star. It's sometimes called cleaning star, but I'm just going to call it star here. So what it is, if we have, so let's just say we have L1 and L2 be languages, then union is going to be written as L1 union L2, which is going to be all the strings X, such that either X is in L1, so it's either in L1 or X is in L2. So for union of sets, you just take everything from both of the sets, just put them together and eliminate duplicates. Okay. Concatenation is slightly different. So that's going to be written L1 with maybe a dot, or maybe just the two languages side by side, nothing in between. You can think of it like multiplication. And that's going to be all the strings X, Z, such that X is in L1 and Z is in L2. Okay. How to visualize which one, Rahul? But union is, yeah, so union is just thinking like Venn diagrams. You're just taking everything in both of the Venn diagrams. And concatenation is totally different because you're working on the individual elements of the sets. Yeah, so the order actually matters here. So it's important that X appear first here because I'm concatenating L1 first with L2. Just as an example, let's just say that L1 was 0 and 1, 0, 2 strings. And L2 was, oh, I don't know, 1 and then 1, 0, 1. So again, 2 strings. So then what we get at the end of the day for the concatenation is we pick something out of L1 because it's appearing first here. So let's just pick the 0. We'll pick both of them, but let's pick 0 first. So then we pick one string out of L2 because it appears second. And then I glue them together in that order. So let's say I pick 0 and 1. That'll give us 0, 1. If I pick instead 0 with 1, 0, 1, that'll give us 0, 1, 0, 1. If I instead picked 1, 0 first, and then 1 after that, that'll give me 1, 0, 1. And finally, if I pick 1, 0 first, then 1, 0, 1, then you can clearly see I'm going to get 1, 0, 1, 0, 1. Okay, and so that's concatenation. Star is basically like concatenation on steroids, but it only works with one language. You can only define it for one language. So the star is going to be written as L1 star, like that, applied to one language, not two. And what it is going to be the following. So it's going to be the union over all k at least 0 of L1, the language, to the kth power. And what that is, what that is L1 to the 0 is the set containing just the empty string, and L1 to the k is going to be L1 concatenated with L1 to the k minus 1. So the idea is that let's say I want to pick 100 strings and concatenate them all together out of L1. Then I set k to be 100. Then what I do is, in English, what this is saying, I'm picking something out of the language maybe the same time, the same string multiple times. I pick 100 strings out of the language and I put them all together in that order. Okay, so, and I pick any number k that I wish, at least 0. Okay, and so if I pick 10 trillion, then I would concatenate 10 trillion strings. Okay. Any questions about that? Rahul, you're jumping the gun on these. Okay, just let me check how many people are watching. All right, the strength of the connection is perfect. Awesome. Okay, I'm getting more drop frames, but we'll just carry on. So we have these operations, and so we have one more operation, which is not a regular operation for some reason, but we have complement, which is for a language. Let's let L be a language, regular or not, it doesn't matter. So then what we're going to say is that L bar, with a little bar on top of it, is going to be the complement language, which is every string in sigma star, take away the ones that are in L. So in other words, this is every string not in L. Okay, so if I had like the string containing, the set containing the empty string, and I form the complement, that will give every non-empty string. So those would be complements of each other. So we're actually able to, with all that out of the way, prove our first thing, which is saying that regular languages are closed under complement. Okay. So why is this true? So why are they closed under complement? The reason is that if we look at a DFA, so let's say that we have some DFA right here. Well, if I want to be able to show this, I better be able to show any regular language. If you do the complement to it, you will get a regular language as output once you do the operation. So here, if we have a regular language, that tells us there is a DFA for it, because that's what the definition of regular language is. So that means if I can find a DFA for the complement, then that'll suffice, because I found a DFA for the complement. So let's actually think about this. So if I have a DFA right here, it has a start state, and let's say there's a final state way over here, and it takes a lot of transitions to go from one to the other. The key to note is that there cannot possibly be some other path that will go to the same state. This is not possible in a DFA, because every single state has exactly one transition coming out of it on every single possible symbol. I'm falling out of frame. Yeah, so it only has one possible way of going. So the key here is, what if we just switch that this state is not final anymore? So if I change this state to not be final, then what could have possibly happened is in the complement, the string before was accepted because it landed in a accept state. But in the complement, every string is either in the language or its complement, because there's nothing in common between them. So if it was accepted before, it can't be accepted now. And if it wasn't accepted now, it should be accepted now. So the idea here is to flip the final and non-final states. Okay. And this works because there's only one possible way of going through any computation. Every string is exactly one computation. But if it just happened to be that there were multiple, then I can't claim this. But because there's exactly one, then I can flip the final and non-final states here, which is pretty cool. All right. Yeah. So let's see. All right. So let's try to handle union. So let's try to do union. So I have two little DFAs right here. So it's Q0 and how do I call it? 0, 1, Q1, which is a final state. 0 and 1 here. Oops. Oh, what is the complement of the empty set? So that's a good question. So the complement of the empty set is going to be sigma star. And the reason you can see this is if you take a DFA for the empty set, so which is something that looks like this with no final state down here, then what gets transformed when we flip the final and non-final states is I'm going to get that this is final, which in it self-loops on everything, which means it accepts everything. You're welcome, PokeFan Games. All right, so let's try to handle union. Yeah, so the other machine, So this is for L1 and this is for L2. So the R0 machine is going to self-loop on 0 and go 1 over to state R1, which is going to loop on 0, and this is going to come back on 1. I'm in class right now and we just learned about Turing machines. I'm going to hit Turing machines in a few weeks for a live stream just like this. Okay, so let's look at a string. Let's just call it 0, 1, 1, just as an example. So if we figure out where it goes in this machine, clearly it starts in Q0. Then after reading the 0, it goes to Q1. And because this self-loops on everything, it's going to stay in Q1 forever after that. So this thing ends in Q1. In this one, the same string, because we want to figure out whether it's accepted by either one of them. Then what happens is we start in R0 because it's the start state. It self-loops on 0, so we go to R0. And then the two of the ones go back and forth between R1 and R0. So it's pretty clear that we should accept this in the union because this first machine accepts it, but this second one, and we don't care what the second one does. It happens to not to, but actually the R1 state should have been final. My mistake. That should be final. But it doesn't matter because we ended in R0. Okay. The problem with this idea of just running one machine, seeing what happens, and then running the other machine on the same input, the problem with this is that once we read some characters, we can never ever go back. So we really have only one shot to read the whole string all at once. So the idea for showing closure under union is to try to simulate both machines at the same time. So a theorem that we'll prove here is that I'm going to shorten it to RLs to save on time. RLs are closed under union. Can you make a finite automaton that accepts phi, which I'm assuming to be the empty set? I've already did that here. And one that accepts only epsilon, then what you can do in that case is just use this machine, but do the complement of it. So make this one the final one, make Q1 the not final one. Okay. But I haven't hit NFAs yet, so just hold your horses. I'm teaching this class in order for a reason. All right. So the idea here is to simulate, quote unquote, both machines at the same time. God, that was written terribly. At the same time, because we only have one shot to read the string here. So what we could do is we can try to record which of the states we could ever possibly be in. So let's look at these two as an example. So I'm going to copy this guy down here. I'm going to do it slightly different than the way I usually teach this to make things easy. So if we try to simulate both things at the same time, then obviously we're in the start state of both. So the way I'm going to notate this is I'm going to make a state called Q0R0 and have that be the start state. Yeah, and then what we're going to do is we're going to try to simulate both machines at the same time by figuring out where the two machines would have went on 0 and where the two machines would have went on 1. So on 0, well, what happens is
Q0 goes to Q1. So I notate in my brain that we're at Q1 now. And then R0 is going to self-loop on 0. So we're going to be in R0. So wherever this guy goes, it's got to notate Q1 R0. So I'm going to have, and I haven't made that state yet, so I'm going to make a state called Q1 R0. And for the 1 case, we're going to still be in Q1 no matter what. And in this case, we're going to go over to R1 because we're in R0 over here. So we're going to be in Q1 R1. Let me move this down a little bit. So then now what do? Well, we still have unfilled transitions, so we got to figure out where this guy goes on 0 and on 1. So let's see. So where does this guy go on 0? Well, the Q1 will self-loop on everything. So no matter what, this is going to be in a Q1 state. The 0 is going to, let's see, we're in R0 now. And on 0, we're going to stay in R0. And we're going to stay in Q1 because that's what the first one did. So we're going to, in fact, self-loop on 0 here. And on 1, you can see that the R machine is going to go back to the other state this way. So then the 1's going to go over to here. And for this one over here, the Q1 state is going to, again, self-loop. So it's going to be either in this guy or this one. And then the R1 is just going to self-loop on 0, so just like before. Or it's going to read a 1, in which case it's going to travel over to here. So, but also we need to figure out what the final states of this guy are. Well, the ones that are going to be final are the ones where either of the 2 machines was in a final state. So any state that has Q1 in it, that's going to be a final state. So any state that has Q1 written in it. So this one's final, this one's final. And any state that has R1 in it is going to be final too. This state does not have R1 or Q1 in it, so it's going to remain non-final. Okay, and we can actually do a sanity check. So the string 011 up here, we verified to be in the union. So is it in the union down here? Well, the 0 is going to come down here from the start state, and then the 1 comes up here, and the 1 comes back down here, which is a final state. In fact, you can see here that there's no transition to this non-final state. So once you read any transition at all, you're going to be in a final state in perpetuity. So the union of these two just happens to be all strings that are non-empty. But it could very well be something totally different. It's just, that's what it happened to be this time. It could even be sigma star for that matter. Okay, so this thing right here is what is called the product construction. Why is that? Because what we're really doing is we're taking the product, in fact I should say what this is, it's the Cartesian product of the state sets. Okay, it's just taking the product of the state sets. Well, you may think, okay, well there are 2 states here, there are 2 states here, but you only got 3 here. Well, shouldn't you get 4? Because that's what 2 times 2 is. It's because there's some state that's just unreachable. Okay, so the state of, what is it? Q0 R1 is just not possible to ever have. Why? The Q0 state, once you have a non-empty transition input, you're going to be in Q1. But in order to get to R1, you have to have a non-empty string. So you would have to simultaneously have an empty string and a non-empty string at the same time, which is impossible. So the way I usually teach this is you have to put every state in here, but here, because of something we'll see later, we're going to allow ourselves to ignore states that are just unreachable because they're not going to change anything. It's like they're completely harmless, but it's a waste of our time. Cool. And the thing is, what about, say, for intersection? Well, there are two ways to approach this. What about for intersection? Intersection. So one thing that you should remember is something called De Morgan's laws, which say essentially that the intersection of two languages or sets is equal to the complement of one union, so the opposite of the two, union the other language's complement, and then the whole thing complemented again. Well, regular languages are closed under complement and union. So that actually tells us, because there's only a finite number of these unions and complements, that they're also closed under intersection too, which is pretty nice. So in fact, we get a check mark on intersection also. The regular languages are closed under intersection. But another way to see it is we could modify, so this is just one way. Another way is to do the product construction and change the final states as necessary. The final states in this case would be all the pairs of states. Instead of where one of the two was a final state, it's rather that both of them were originally final states. So in the above example, for intersection, the only one that would be final ever is R1 and Q1, which is this one right here. So for intersection, this one would be excluded. Cool. So that tells us that regular languages are closed under intersection too, which is pretty nice. Okay, so let's try to handle concatenation. All right, how are we doing on? How's everyone doing, by the way? Just let me check YouTube analytics. Good. Good to hear, Rahul. Okay. So what about for concatenation? Well, this was L1, L2 concatenated together, which is all the strings X, Z, where X is in L1 and X is in L2. So the question is, are regular languages closed under concatenation? So that's the question we want to answer here. Because if you think about it, the regular operations are just thinking about the problem in terms of smaller subproblems. So like for union, if you can solve both of the two pieces, then you can solve the union. Here is asking, if you have two languages that are regular, that are smaller, I'm concatenating them together to get a bigger language, is that one regular too? So the question is this in fact regular? So if I have a string W1, W2, up to, let's say, WI minus 1, WI plus 1, up to WN, what we're asking is it simultaneously the case that this piece right here is in L1 and this piece over here is in L2? So those are the main questions that we want to answer when we're looking at concatenation. The only issue with this is, oh, there's several, but the big issue is, where is this split between what is in the first part and what is the second part? There's no marker to tell you, oh, just switch over to the other one. So the thing is, you kind of have to think, you're gonna have to instantly jump from one machine to the other one. And that seems quite difficult. So the way that we handle this in mathematics and computer science is we try to look at a generalization of the problem and then see if that generalization makes sense for the problem that we're considering. It may or may not make any physical sense to talk about it, but it makes sense from a problem-solving perspective. Okay, so what I'm going to start talking about is a generalization of DFAs which allow for them to not be deterministic. Okay, and of course it has a name. It's called a non-deterministic finite automaton, or NFA. And what it has are any number of transitions from any state. So instead of having exactly one for each character, you can have any number that you wish of every character. And also, we can have something that is special, and I'm going to change the color, something called an epsilon transition. And what this is if taken, no character is red. Nothing is red on that transition. Okay. So just as an example, and I should say, so what does the non-deterministic mean? So what this means is if some way to make choices to end in a final state, we will accept. Okay, so that's what non-determinism means. It's not like random, because that's wrong, at least in this context. It means that if there's any possibility of making choices to land in a final state, we will make those choices to land in the final state. Okay, it will always make one choice. So, always one choice at a time. Yeah, epsilon transitions are basically jumps. Yep, exactly. Yeah, so it's all right. So we have these. We have all this here. So we can talk about the language of the machine. It is very analogous. There are some caveats if you want to define computation formally, because of these epsilon transitions, because you can have more states along the way than you normally would see in a DFA, and you have to read the whole input, just like in a DFA. But the thing is, the number of computations could be anything. So let me show you that. So the number of computations can be anything, as well as any number of accepting ones too. So just as an example, so if I have something that looks like this, so if I have this example, then I could take this self loop right here, which has epsilon written on it, and as many times as I like. So at some point then I choose, okay, now I choose to use a 0, and that will get me to Q1 and accept. Let's say the input is just 0. But then there are infinitely many ways of taking this self loop right here and then moving over. So it's not that we don't have this nice property that the DFAs had anymore, where you can flip the final states and non-final to get the complement language. So it won't work with NFAs, but it allows us to do the regular operations really quickly. So let's do an NFA or NFAs for the regular operations. So remember, the three operations are union, concatenation, and star. So for union, what we can do is something really clever. So let's say that we have 2 NFAs. These could be DFAs, it doesn't matter. And let's say they have a start state here, here's another NFA. Then what I could do is to have a brand new start state right here and epsilon transition our way to the previously start states of both machines. And this gets union because whichever one, if it is in the union, then one of the 2 machines will accept, which means by non-determinism, it'll make the right choice to either go up or down here, which is nice. So it gets union really quickly. What about for concatenation? So for union, the order didn't matter, but for concatenation, it does. So I need to have 1 NFA first and 1 NFA second. So let's say that this guy has a start state and maybe 2 final states. This guy has a start state and maybe 3 final states. So then the idea was that we need to be able to jump instantaneously from the first machine to the second one. But now we have that mechanism, which are the epsilon transitions. But I only want to go from the ones that are final states in the first one, because I want to read a string that the first one accepts and then jump to the second one where it reads the rest of the string and maybe accepts. So I need to have epsilon transitions only from the final states over here. And I need to make them non-final, because if I have a string that just L1 accepts, that the first language has, then if I make these final, then I can stop here because I don't have to take this transition coming out. So then the idea was that we need to go through both machines in their entirety. And if I'm allowed to stop early, then that's not the union. Okay, so what about for star then? For star, then remember for star, it was just a single machine. And let's say it has a start state and 2 final states. Then what we want to do is, once we go through the machine, we pick a string out of the language. We want to be able to go back through again as many times as we want. So the idea, although this is not right, is to have an epsilon transition from here to the beginning. There's actually a problem with this, mainly because in the star of any language, the empty string is contained in there. So let's see, look at the questions. Are you going to show pumping lemma eventually? Unlike the DFA, there can be 2 final states in the NFA which accepts the same string. Yeah, exactly. You can even have one state that is final and another one that isn't final with the same string going to both. That's totally possible. Okay, how the machine will decide which way to go? Great question. The thing is, we don't know which one it'll pick, but it will always make the right choice if there is a choice, if one of the choices leads to going to an accept state. So it's kind of like having some clairvoyance as to what will eventually happen. You can see that this can't be built in real life, but we define this because it's really easy for these problems, whereas the DFA is really difficult to do. Okay, so the NFA comes back here, but the problem is the empty string is always in the star of any language. But then that would mean I would have to possibly make this state an accept state, but that might change the original machine's language, and I don't want to do that. So the idea is to not do this, but instead make a whole start state out here that is an accept state itself, epsilon transition your way in so that the behavior of the original machine is not changed, and then epsilon transition from these states either to this state here or to go to the brand new one. I choose to go to the brand new one. Either way is fine, purely because I'm not modifying anything internal to the original machine there. Okay, so that actually shows that the languages of NFAs are closed under star, union, and concatenation. It does not show that the languages of DFAs are closed under those three. We did union, but concatenation and star we have not shown. So what we're going to do is we're going to, after a little short break, is we're going to talk about what is the relationship between NFAs and DFAs. Is there a way to convert an NFA to a DFA? Because every DFA already is an NFA, because the NFA doesn't have to be non-deterministic. So every DFA already is one NFA. It's just not every NFA can be a DFA because of the epsilon transitions and non-determinism. So I will, star one, please explain more. So here, I need to have a way of going back through the machine as many times as I want. But I can't come back here. Why? Without this state. I can't come back here because I need to make the start state or something like it be an accept state. But in order to do that, I might actually, by changing this to be an accept state, I will potentially change the behavior of the original language itself. So, like as an example, if I have like the start state being here, and then A going back and forth between another state, and then maybe B going somewhere else or something. So then originally it didn't accept AA, two A's, but if I am forced now, because the star of any language has the empty string, I'm forced to make that state a final state. And then now it accepts AA for the original language, which I didn't want to occur. Okay, so that's the reason. Okay, so I'm going to take a short break, and we will be back in showing connections between NFAs and DFAs. Okay, so I need a snack. All right. So what we want to do at this point is we want to understand the relationship between NFAs and DFAs. Thank you, 92 Jiv. Okay, so we want to understand the relationship between NFAs and DFAs. Well, one thing we can immediately see is that every DFA is an NFA. There's a slight technical reason why they're not, but it's very easily fixed, and I'm not going to go into it. But yeah, NFAs don't have to have non-deterministic behavior, but they could, so it's not the case that every NFA is a DFA. So we need to be able to work with that. So if we have an NFA, how could there possibly be a DFA for it? Or maybe there might not be. So let's look at a potential NFA here. So I have an example that I've cooked up. So Q0, and it could have epsilon transitions. So Q1 here, then A, Q3 has a final state, then A, Q2, self loop on B, make sure it all fits, yeah. And then epsilon here, and then here is B. Okay, so this is obviously an NFA. So how do we actually, could we possibly make a DFA for this? So I'm going to move this over. So then if I want to make a DFA for it, I need to have a start state just like before. And then what I need to do is I can't have epsilon transitions at all. So it needs to have an A and a B transition going somewhere. Okay. So the thing is, remember that an epsilon transition is one where you can take it and you don't have to read anything. So at the very beginning, before we've read anything, we could slide on over to Q1 if we wanted to. But no matter which one of these two that we're in, there's no way to keep going after that to accept more things. Sorry, to get to more states. So like Q1 has no epsilon transition coming out. Can epsilon be considered in sigma? No, it can't. Good question. The reason why is that if you concatenate two things from sigma, you must have something that's longer than the original ones. And in alphabets. But if you concatenate epsilon with itself, you still get the empty string. So it can't be in there. Good question. Okay, so A and B coming out here, we don't know what necessarily. But what I'm going to do is, no matter what happens, we're either going to be in Q0 or Q1 at the beginning. I can't get anywhere else before reading anything. So what I'm going to do is I'm going to have a state that I'm going to call Q0, Q1, meaning the states that I can get into at the beginning. So then, of course, I have an A and a B that can, I need to figure out where they go. So the thing is, remember that NFAs make choices. Always one choice, but it makes choices. So this is basically simulating the machine in parallel. The machine itself, the NFA, does not work in parallel, but we're simulating it, quote unquote, in parallel, although it's not really in parallel. So we could either be in Q0 or Q1. I don't know which one it's going to be in advance. So what I'm going to do then is, let's just assume it is in Q0, just as an example. Then if we try to read an A on there, note that there's no transition coming out of it on input A at all. So the Q0 contributes nothing to this transition here. But if we look at Q1, it does have transitions that are labeled A, right? So, and namely Q3 and Q2, okay? So the only states that I could ever get to from this pair, although it doesn't have to be a pair, is Q2 and Q3 from the transition alone, the reading A alone. But it could be that once we do this, then we could follow some more epsilon transitions. Because we are encountering new states, we might see more epsilon transitions. The only one that is apparent here is the one that goes from 2 to 3. So we could theoretically take the 2 to 3 transition here, but I've already included both states, so it doesn't actually matter. So so those are the only two states I can visit from reading A from either one of these two states. All right, so what about for B? Well, Q0 goes nowhere on B. Q1 also goes nowhere on B. So the set of states that I can reach is empty. So the state that I can go to then is called, I'm going to call it the empty set, because it's the set of states that I can go to here, but there's nothing I can go to. It's just like any one of these other states, but yeah, it's just a certain set. This is a set of states, this is a set of states, just like this one is. So for the empty set, if I'm nowhere and I read an A or a B, then I can't go anywhere else because there's no transition of any kind here. So this is actually going to self-loop on A and B. Because once you're nowhere, you can't go anywhere else. What about from 2 and 3? So from 2, let's look at what happens on input A and B. So from 2, I can't go anywhere on A, and 3, I can't go anywhere on A either. So in fact, this transition, just like the other one, goes to the empty set state. And we've already made it, so I'm going to have it just go straight there. What about on B? Well, Q3 goes nowhere on B, so I don't need to do anything for it. Q2 on B, well, it goes to Q0 and itself because there's a self loop here. So I'm going to include those two in the list, in the set. But we note that once we're in Q, if we choose to go to Q0, then I could theoretically go over to Q1. So Q0, Q2, Q1. And I can't go anywhere else based on the earlier discussion we had. So where do we go on A and B from this state? Well, we can see that it's going to do something kind of similar to this one up here, because the Q2 state has no A's coming out of it. So what it's actually going to do is the same thing that this state up here did on input A, because the 2 contributes nothing to the transition in total. What about on B? Well, Q0 and Q1 don't go anywhere on B at all. So the only one that matters here is Q2. And where did Q2 go on B? Well, we've already done that work. It's this state. So in fact, this state is going to self-loop on B. And I've completed every single possible transition from these states. I didn't encounter any new states that I don't have transitions for. And so we're totally done. Other than making final states. So for the final states, it's the ones that, remember, have a choice of going to the final state, if there's any choice at all. So this state can't be final because neither one of these two states is final. This one is going to be final because Q3 is. So I'm going to mark this guy as final. And this one down here is YB from 2, 3 did not go to 0, 1. is because of this self loop down here. This self loop added Q2 into the set down here. So this was included. Okay, so yeah, so this state's final. This one's not final because there's no Q3 in there. Okay, so this is a construction that's called the Powerset construction. Why is that? Because it could theoretically be that any one of these states could be any possible subset of the states. Okay, we only looked at 4 possible subsets of the 16 that are possible here, but it's just that those other 12 are just not possible. So like, just as an example, being in all 4 states simultaneously, that's just not possible because we did kind of like a breadth first search or depth first search, I guess, of the set of states, the set of states I can go to. And we were only able to see 4 in this case, but there are some cases where you need all possible state sets. And this was mentioned in the chat earlier. If you have n states, you could theoretically have 2 to the n possible states in the corresponding DFA. So remember, this thing is the NFA, and this thing right here is the DFA. Okay, cool. So that idea works in general because we can compute for any set of states where we can go from epsilon on only epsilon transitions. That's something called epsilon closure, and I have many videos on the channel talking about this, but so I'm not going to go over it here. It's not really that important. The important thing is being able to make the conversion from NFA to DFA. It's looking at where you can go on epsilon at the beginning, making that the start state, then looking at each of the characters, so like A and B in this case, recording where you can go, as well as after that, where else could you go on epsilon transitions. Okay, so that's so therefore what we can say is that the NFAs are equivalent to DFAs in that they can compute the same things. Because if I do something with an NFA, I could just convert it to a DFA using this idea. Or if I have a DFA, it already is an NFA, so I'm already done. So they're equivalent to each other. So for NFAs, they basically force you into a state. I don't know what that means. I don't know what forcing into a state means. With DFAs, they're forcing you on the transitions, whereas the NFA, you can have choices. But yeah, so I'm not sure what you mean there. Okay. Let's see. Okay. So we are ready to move on to the next thing. So we're about halfway through, I would guess. Like how you can't have a state with the same transitions in an NFA. Well, an NFA can have any transition from anywhere to anywhere else, and as many of them as you want. So, like how you can't have a state with the same transitions. Okay, so yeah, an NFA can have the same transitions from any state to any other state. Yeah, so it's basically a wild party where everyone can send transitions to anyone else. But a DFA, there's a restriction that you can only have one other state on a particular symbol. So like on 0, it can only go to one state, whereas an NFA could go anywhere. Yeah, you can do anything really. Yep, exactly. Okay, so we're ready to move on to the next thing. it's on the final state and there's some characters to read, but you have no transitions there. So you remain on the final state. Oh, okay. Okay. So that's something I should clear up. So if we have something that has a transition to a final state, and there is no transition coming out of it, if we end up here and get stuck, what happens? Well, the criteria for accepting a string is you have to be in a final state and you have to read the whole string. You can't be partway through. Okay, so if I'm partway through reading and I'm stuck here, then I'm not going to accept at all. Uh-oh, lag. Yeah, the number of frames dropped jumps at random times. It might be my internet connection. I'll try to make this as clear as possible. If you have any questions or want me to repeat something, I can do that. Okay, so let's talk about the next thing. So what DFAs and NFAs do, what they do is they accept a language. So you provide a string to them. Yeah, so we provide a string. It computes by going between states and whatnot, and says accept or not. Right, and that works just fine. But the thing is that it doesn't give a real reason why a string is accepted or is not accepted. So, and yet another thing might be, if I try to describe a language to you, so if I say the language, which is all the strings in 0, 1 star, such that the number of 0 1s in W equals the number of 1 zeros in W. Then the thing is that English is a very terrible language. No, I mean that it's not precise at all. So just writing this in this hand-wavy notion of what number means, the number of something in a string, that's kind of not very precise. So what we want to do is to be able to describe a language precisely. So what we want to do is to describe a language precisely. And that is the job of something we're going to learn, which is something called a regular expression. So a regular expression is one of 6 forms. So let's let sigma be an alphabet. Then the regular expression can be one of 6 forms, just like I said. It could be, okay, let me do it this way. So I'm going to move these down to the bottom of the C. All right, so then we say a regular expression. R is one of the following, which is it either can be equal to the empty set, it could be the empty string, like the actual writing of it is the regular expression. It could be a single terminal. It could be a single character A. So A is a character in the alphabet. It could be that R is the union of two smaller regexes. So here we're going to say that R1 and R2 are regexes. It could be that R is the concatenation of the two, or it could be that R is the star of one of them. Okay, so you see where this is going probably, that we have union, concatenation, and star, and you say, okay, well, regular operations are going to play a role here. And in fact, they are. So I could, just as an example, have something like 0 union 1 star 1 0 1. So this is combining union clearly, it has star clearly, but it also has concatenations. So each of these, 1, the 0, and the 1, are all individual regular expressions. And there's a concatenation that's happening in between them. So this is a regex. This is saying that we have anything that can occur. So this is saying you can pick zeros or ones as many times as you want until you choose to stop doing that, and then decide to go to do this part right here. So this is actually a regex for all strings ending in 101. Okay, because anything can appear before as long as 101 appears at the end, because there's nothing after this last one here. Yeah, 01 star is something different. So 01 star, no union inside. So this is going to be all strings of the form 01, 01, 01, etc. And it must end in a 1. That's kind of easy to prove, because if it ended with a 0, that means that we must have went in here at least once, but that means that because there's no union in here, we read the 0 and the 1 before we actually can go back through if we wanted to again. So all strings in here either start with a 0 and end with a 1, or are the empty string, because this says we can pick it 0 or more times. So yeah, so remember that star means at least 0 times. Okay, it could be 0, which means we don't actually pick anything out of there. Okay, how are we doing on this live stream? Just checking analytics. All right, so we're doing good. Yeah, so we have regexes here, and we could define the language of them very analogously. So like if the regex is the empty set, then it's just the then the language is the empty set. The language of this one is just the empty string. The language of this one is just a single string A, nothing else. These three are the union of the languages of these two, concatenation of the two, star of this one. It's like I'm going to class again, thanks. Abdul Rahman, thank you very much for watching. Okay, so let's see. So it's called regular expressions, and there's a lot of misinformation out there, because there are some regular expression engines that are more powerful than this. But it turns out that we can actually convert between a regex and either a DFA or an NFA. So a theorem we'll prove is that NFAs and regexes, regular expressions, are equivalent. Which means that I can convert from one to the other and back and forth. Okay, so it's actually kind of complicated because the regex can have a lot of structure, and the NFA could be whatever. It could be really anything. So we actually do this in two parts. So the first one is, I'm going to use a lemma for this. So lemma just means little result to help prove a theorem. Okay, so it's just to help to prove a theorem. So what we're going to do here is every regex can be converted into an NFA. And then later we'll do the opposite direction. We can convert an NFA to a regex, but we're going to do this one here. So the idea is we're going to look at the definition. A lot of things in this class are based on the definitions. If you understand the definitions, you are golden. So if we look at a regular expression, R, it could be one of those 6 types. So 1, 2, 3, 4, 5, 6. Let me move this over. Whoops. So 3, and then I'll move this over because I need some more room. So if R is equal to the empty set, do we have an NFA for the empty set? And we definitely do. That one. I don't have to have any transitions, and if it has any non-empty length, it can't go anywhere, and it's not an except state, so we're all good. What if R is equal to the empty string? Then we can actually do something really similar by making that state to make it a final state. And this is actually a proof that if you do the closure under complement thing for NFAs, you will fail, because these two are not complements of each other. Because this has 0 strings in its language, this has 1 string, and yeah, they can't be complements. What if R is equal to a single character? Then what we can do, we can't get away with 1 state, but I can get away with 2. Which is that we can't have the start state being final because I don't want to accept the empty string in this case. And then if I read an A and go to a final state with no other transitions, the only way I could ever accept a string is if I read just A and no other characters later. So that shows that we can make a little NFA for this regex. What if R is equal to the union of 2 smaller ones? We've already done this. So if I made an NFA for either one of these two, then I can make that new state and epsilon our way to the old start states of either one of them. If it's the concatenation of 2 of them, we have already done this. To put the 2 NFAs side by side and having the final states of the first one feed into the start state of the next one with an epsilon transition. And for the 6th one, if it is some regular expression starred, then that's essentially asking, can I make the star of an NFA? And what you do is you have that extra start state where we epsilon transition back to that start state, which is pretty cool. So let's actually do an example, because a lot of students mess up this one. So let's do an example, which is 0 union 1 to whole thing starred. Okay. So the way to look at this is, because of how the definition works, we're working on a recursive structure, because there's some base cases right here and some recursive or inductive cases. So what I recommend doing here is to focus on the really small regexes and try to build bigger and bigger ones off of those in terms of NFAs. So what I'm going to do is I'm going to build a little NFA for each one of these individually. So I can make one for just a single 0 and nothing else. I can make, that was bad. I can make an NFA for just the single 1 and nothing else. I can make one for 2 and nothing else at all. Okay, so then now we did each individual piece. So now we did all the base cases. Now let's handle the inductive ones. So note here that there is a concatenation happening between these two. Oh, thank you, Not Poke Fan Games, for your donation. If you want to donate, there's a link in the video description to do so. PayPal or something in the YouTube chat. I know there's like super stickers or things. If you want to donate, you're free to do so, but you're never required to do so. But thank you for donating. Okay, so let's look at this right here. So 1, 2, those are individual regexes. So I can't just say, oh, the 1, 2, that's going to be this. So 1 followed by 2, like that. Because I need to treat these as individual regexes. This is a totally valid NFA for this, but it's not correct in terms of the conversion to make sure it works in general. So I can't do this. But what I can do is follow the recipe for doing the conversion, which is, let's make the NFA for 1. We've already done that. So I'm going to copy this over to here. I'm going to copy and paste the NFA we made for 2. And following the recipe, I make this state no longer final. And I epsilon transition from all the final states of the first one on an epsilon transition to the start state of the next one. And so that's the correct way of thinking about it. That I don't have to be clever about this. I can just copy and paste what I've already done into it. Okay, what I'm going to do here is I'm going to work on this little NFA right here all at once. So instead of building it up in stages, I'm going to do it all at once. So now we've done this part right here, the 1 and the 2. So let's do the entire thing inside the parentheses, which is including the union. So it's the union between the thing we just did and 0, the NFA for 0, I guess. So I'm going to copy and paste this guy down here. Oops, I accidentally copied part of the 1. And what I'm going to do is follow the recipe, which is make a new start state and epsilon transition our way to the old start states. It's just following the recipe. And now the only thing that's left to do is to handle the star. And we've seen how to do this before, which is to first move this over. And then what you do is you make a brand new start state that is final. You epsilon transition your way to the old start state. And from all the other final states over here, you're going to epsilon transition all the way back to the blue state at the beginning. So they're all going to epsilon transition over. And there we go. So that is, in fact, a NFA for this regex. Is working with the definition of what the regex actually is and being able to build a little NFA for each one and then start combining them with the regular operations that we've done before. So that tells us that every regex can be converted into an NFA, but we haven't shown the other way yet. Cool. All right, so let's try to think about how would we show the other direction. So here's a lemma. the second lemma, which is every NFA can be converted into an equivalent regex. Will this be posted on Discord after? If you're subscribed to the channel itself, you'll see it. I could post it on Discord after. If I don't, just ping me and I'll post it. All right. So let's see. So we want to show that if it is possible to convert every NFA into an equivalent regex. The thing is that the NFA might not have this a really simple structure where we could just, okay, we see the union happening here and the star happening here, and here are the individual regexes, and we can try to extract it out. Oh, don't worry about interrupting, that's fine. But we can't just extract it out really simply like this. Because the NFA could have weird structure, like a self loop on here, potentially. In fact, this actually tells us something interesting, that every regex can be converted into an NFA that has no self loops on any state, which is kind of weird if you think about it. No self loops, but either way. So the thing is, well, we can't do something like this, which is have a single state that goes to a single final state, and have the regex R written on the transition, which is kind of annoying, right? We can't actually do this because we can only have one thing on the transition at a time. That is until we will generalize it here. But unfortunately, that's what we can't do this. But if we can make it so that this does happen, or something close to it, then it makes sense. So what could we actually do here? Let me pull my notes up. Okay, so let's see. So if we actually think about this, well, what are the possible things that can happen in terms of getting down to two states? Well, the NFA very likely has more states than two. So if we want to whittle this down to two states, well, we got to do several things. Well, one thing is the NFA can have any number of final states. So what we can show pretty quickly is that every NFA can, without loss of generality, that's what W log stands for, without loss of generality, can without loss of generality have exactly one final state. And the basic proof of this is really simple. Is you have a little NFA here, and let's say it has 3 final states, just as an example. Then what I'm going to do is I'm going to have a brand new final state, and have the old ones be no longer final, but epsilon to it from them. So it's kind of like the concatenation idea. You make them no longer final and epsilon your way over. But here it's going to a brand new final state. And so we can assume that there's exactly one final state here. But we can also assume, so without loss of generality, have a start state with no incoming transitions. We can assume that without loss of generality. And why is that the case? That's kind of like the star idea that we had, but a little different. Here, what we can do is have just a brand new start state, not a final state, and epsilon your way into the old start state. And this clearly has no incoming transitions, even if this one did. So the thing is, well, now we kind of have this state that's kind of required, and this state that's very obviously required. So these states in the middle, if we can kind of simplify the states in the blue part right here, then in the sense that we get rid of them and not change the language of the NFA, then as long as we don't change the language all the way through, then at the end we'll have a much simpler machine with these two states, because I never touched them, that will have the exact same language as the original one, and maybe we'll be able to extract a regex out of it. So the idea is to make the NFA simpler. So if we look at this so if we try to get rid of some states in here, well, what could possibly happen? So let's say that I have A goes to B on some regex R. So I know we can't do this in an NFA, but let's just assume that we could. Then clearly this regex might be totally useful. So I might not be able to get rid of this. But what if I had something like A going to B, which is going to C, and I want to remove this one? Then let's just say it's R1 and R2 on here. So then what we can do is we can transform this into a single transition which has R1, R2 concatenated onto it. Because in order to get from A to C, we need to do something with respect to this regex right here, and then something with this regex, but that's just concatenating them together because there's no self loop here. Okay, what if we had a slightly more complicated scenario where we had A, B, and C? But B has a self loop, so R1 on the first, R2 on the second, R3 on the third. Then what will happen is the way to represent this, which is going around as many times as we want, at least 0, we know at least 0 means it's the star. So we can transform this again into a single transition, which is R1, R2 star, R3. And if we make this a little bit more complicated by having a direct transition from A to C, so let's call it R4, then it could be that we take this this R4 route, or we take this longer route with these three transitions. And in terms of regexes, to represent them using OR is with union, of course. So if I do that, then I can modify this regex right here to be what we have before. Either we go over the top route, or we go over the bottom route, or I guess under the bottom route. Okay, so if we have this, we have one fewer state in the entire machine, and if we just keep doing this, then we will eventually get down to those two magical states. So what we want to do is to be able to look at this type of machine. So this thing is called a generalized NFA, which means that every transition is a regex, and nothing going into the start state, nothing leaving the one final state. Okay, there's nothing leaving the one final state. And I actually just remembered, I'll post these the notes that I'm doing onto the Discord server. So if you're not on the Discord server, the invite link is down in the description. Okay. So what are we gonna do here? Well, what we are gonna do is we're just going to repeatedly do this operation over and over, and that's it. So yeah, this process is just repeatedly, and the term for this is rip, and the meaning of that is delete a state, and what we do is we add any transitions as necessary to ensure that the language of the machine is unchanged. Because if you look at this, this transition right here does exactly the same thing as these sets of transitions right here. It's one transition that encodes multiple transitions here. Okay, and then what you do is at the end, the generalized NFA will be of the form it's going to be a start state going to the single final state because we removed all the other ones, and with a some regex on there, and so the equivalent regex is in fact R. Okay, and as long as we ensure that we rip the states out in the correct way, then that's all that we actually will need here, which is pretty nice. So let's do an example. I've like at least 4 whole videos dedicated to this conversion. So if you don't get it here, look at my most popular videos on the channel. But let's do actually an example of this. In fact, let's do, where's an example? Where's a smaller one? Yeah, let's do this one. So I'm gonna copy this NFA that we made earlier, and I'm gonna come down here, paste it. So we need to first fix the NFA to have that one final state with nothing leaving it, although it is true here, but it's just a good idea to get into practice of doing it anyway, and to have a start state with nothing coming into it, which we definitely need to fix. So here, let's have a new start state. I'm going to call it S, which is going to go into the old start state on epsilon transition. And I'm going to have a new single final state I'm going to call F, which is going to epsilon from all previous final states over here, but there was only one. Okay, so now we need to start ripping or deleting states. And it technically doesn't matter which one you pick as long as you do the ripping in the correct way. So the one that is usually the easiest is the one that has very few transitions coming in or leaving. So the way that I do this, and you can do it any way you want, is I make something called an in, an in and an out list. So here I'm going to try to rip Q3 because it seems pretty easy to me. Although Q0 is perfectly fine too. It's just we gotta handle more potentially. Okay, so we gotta, in the in list is going to be all the states that go into the thing that we're ripping, which is 3. So Q1 goes into it directly, and I mean this in a direct way. In a single transition does it go in. And Q1 it definitely does, Q2 it definitely does. So Q1 and Q2 are going to be on my in list. And on the out list, you may have guessed, that's where Q3 leaves going somewhere else to. So that's going to be F. Here. So the way that we handle this is we pick one state in the in list and one state in the out list for all possible choices. and we will make a transition for them. So let's make one for Q1 and F, which means that I'm going to have a transition from Q1 to F here. Actually, what I'm going to do is I'm going to have this down here. I'm actually going to do all of it in one shot, hopefully. So let's see. Let's redesign this so it has more room. So, so here I'm going to have epsilon s over here because I'm not going to touch it otherwise. Okay, so we're going to have a transition from 1 to F. And so now we need to figure out, how did Q1 go into Q3? Well, we had an A on there. Was there a self loop? No, there wasn't. And so there's no star. And then epsilon over to here is the final thing. So here, in fact, what we'll have on this transition is just A and nothing else. And then now what we need to do is to handle the other pair, Q2F. So how did we get from Q2 into Q3? Well, it was epsilon, nothing red, no self loop on 3, and epsilon to F. So at the end of the day, we're going to have a single transition from 2 to F, which is an epsilon transition. And because we handled all pairs in here, both of the pairs, then now I can actually delete Q3 in its entirety, because that's the state I want to rep. Okay, let's move this. And I'm gonna move you all up here so I have some room. Okay, so let's rip, you can pick any one that you want. I think Q1 looks pretty appetizing to me, so I'm gonna pick Q1. So I'm gonna again make my in and out list. So here, what are the things that go into Q1? Well, it's just Q0 and nothing else. And Q1, where does it go to? It goes to F and to Q2. So Q2 and F. So let's start handling the pairs. So Q0 going to Q2. How did we go from Q0 into the thing that we're ripping, which is Q1? It was an epsilon transition, so we don't read anything. There's no self loop on Q1, so there's no star. And then how did we get from 1 to 2, which is our destination right now? It's just a and nothing else. So we're going to have a straight shot from Q0 to Q2 on the concatenation of those two things, which is just A by itself. All right, so let's do Q0 to F, which is the other pair. So there's no existing transition there, so I'm going to put it like this. And what's going to go on this? Well, you can see that it's going to be exactly the same as before. So it's just going to be a single A and nothing else. Because is epsilon coming in? Because that's the pair that we picked. No self loop and A coming out again. So because we handled all pairs involving Q1, I'm going to now delete it. And actually I can modify this A transition to be a more direct straight line to make it look nicer. Okay, so then now is where things get a little interesting. Let's see. So then now we got to pick a state to rip. Now it's sufficiently complicated, you can actually pick either one. It doesn't actually really matter. So let's rip Q2. So I hate Q2. Let's make our in and out list. So then what are the states that go into Q2 from somewhere else? It's only Q0 because Q2, it does have a self loop, but we're only counting it from somewhere else because we got to start the transition from a state that's not being currently ripped or deleted. So the only thing on the in list is Q0. And on the out list, Q2 goes to Q0 itself and to F. So we will have a pair like this one, which is going to be Q0 going to itself. That's totally possible. So this will be a self loop on Q0 because it goes from itself to itself. So how did we get from 0 into 2 and back to Q0? Well, we have A coming in. Here we do have a self loop, so we represent that by B star because the B is on here and then star on it. And then finally a B coming back to Q0. So the self loop is going to be A, which is coming into Q2, B star, which is the self loop part, and B at the very end, which is nice. What about Q0 to F? So we already have a transition here. So what we're going to have is it's going to be union something, whatever that may be, which is basically going down this route, self-looping on Q2 and taking the straight shot to F here. So that's A, B star, and then epsilon concatenated doesn't do anything. So it's going to be A, B star on that transition. And since we handled everything involving Q2, we can actually delete Q2 now. Okay, so pretty obviously there's only one state to rip now. So rip Q0. And in fact, on this last one, I don't even do it. I don't even make the in and out list because there's only one thing coming in and one thing leaving. So, and it can't be any other way. So that's pretty much done. So what we can do is let's just do it straight to the end result. So it's going to go from S to F. Well, what's going to be on it is epsilon concatenated with stuff. So epsilon concatenated with stuff does nothing. Then this is the self loop. So that whole thing is starred. So it's going to be A, B star, B, whole thing starred. And then concatenated with this. Now, since there's a union here, we need to put parentheses around it. It's kind of like concatenation is multiplication, union is addition. So I need to put the addition in parentheses. So here I need to have parentheses A union A, B star. So then the final regex then, oops, I'm in a different color. Let's see, let's do green. So the final regex here is going to be A, B star, B, whole thing starred, A, and then concatenated with A union A, B star. Not the whole thing star. Whew. That was pretty good. So, yeah. So if you rip them in a different order, you may get a totally different regex, which is totally okay. It's just that there are many possible regexes for the exact same language. And so it could be that it looks totally different from this, but as long as you ripped everything correctly, then it doesn't really matter. There could be so many different regexes, even for the same NFA, even if it's really simple. Okay, so that's good for right now. I'm going to take a short break, just like before, and we'll start with the pumping lemma stuff. So I'll see you all then. All right, so I think we're ready to continue with the fourth part of what we're going to do today, which is we're going to show that some languages are in fact not regular, which is pretty cool. So that means that there's no DFA or NFA or even regular expression for them, or at least the definition of regular expression here. All right, so the question that I want to ask, which is a totally independent question, or it's not really totally independent, is suppose that W is a string accepted by a DFA M. Okay, so suppose it's accepted. The question I want to ask is, what other strings are also accepted? So you may think, okay, well, one string doesn't really tell us a whole lot about what other strings, whether or not they're accepted by the DFA or not. And of course, this idea can be can be worked with NFAs and regular expressions. It's not unique to DFAs, but it's just it's convenient to think about it in terms of DFAs. So let's actually try to think of this as a thought experiment. So if it's the case, so let's say that we're reading W and we're reading a whole bunch of stuff, and we encounter a state, and we eventually come back to that same state at some later point, maybe as a self loop or a lot later or something. And then at some point later, of course, I'm assuming that W is accepted by the thing. So eventually it must hit a final state at the very end. So one thing that we could notice is that if I read a different string, which is going along this route and just skipping this loop entirely, and then just going straight to the final state, that's a different string, but is also accepted, assuming that this loop actually exists, which it might not. We could also go into here and take two loops around. It's a different string. It's not the same string, but it's different strings. But I can go twice around if I wanted to, and then back over. Or I can go 3 times around, or 4 times around, or whatever I want to. So as long as there's some loop in here, that happens. So, so if the loop exists, in fact, we can show that there are infinitely many other strings are accepted, and that totally makes sense. Yeah, if a loop exists, I should add a caveat here, that leads to a final state later. So if there's just a loop, which actually there has to be a loop in every DFA, but it's just that it might not lead to a final state. It could be a dead state, for example, one that is not final and it self loops on everything. Okay, so if it exists, this is the case, but and we know that it exists, but it may not exist that leads to a final state. That's the key. So the question then is, when can we guarantee such a loop? Or if it is even possible at all. So the key insight here is to note that if we have, let's say, 100 states as an example, then if I feed in a sufficiently long input, sufficient meaning over 100 characters, then it turns out that we will repeat a state at some point. Because remember at the beginning, we always will start in the start state. And that means that the number of states that we'll see is one more than the length of the string itself because of the start state at the beginning before we've read anything. So if we have 100 states, if I feed in a string of length 100 exactly, then we will see 101 states. But if there are only 100 states, then that means that some state must have repeated, or maybe many repeated, but at least one of them repeated. Okay, so if generalize, if we have n states and I feed an input of length n, then I will see n plus 1 states, and so I must repeat a state. But it's not limited to feeding inputs of exactly length n. If I feed any input of length at least n, and it leads to a final state, it's accepted, then we will still see the exact same behavior too. So this tells us something interesting. So for any string in L with the length of W being at least the number of states in the DFA, yeah, so if that's the case, then we get this behavior. So let's actually look at this in a little bit more detail. So if I have this DFA right here, which has the start state, that repeating state in the middle, and in fact, this state that's repeating in the middle could be the start state. It doesn't have to be different, but I'm drawing it as if it is. And there's a final state somewhere. They could all be the same state. They don't have to all be different. But we have some number of transitions that take us from the start state to there. There could be repeats along the way. I don't know for sure. What I'm going to do, and there could be some part that loops from that state in the middle and eventually comes back to it because I'm deeming it as the state that it repeats. And eventually that state must go to a final state because I assume that the string is in the language, which means it's accepted by the DFA. So what I'm going to do is I'm going to label each one of these pieces as X. That's the name of the string, the set of characters I read along that route. So the first piece of it I'm going to call X. The second piece I'm going to call Y. And the third part I'm going to call Z. So we can note here that W itself is equal to X, Y, Z because it's just reading the parts in order. But we can see that XZ is in L because if we just follow the paths, X goes to the repeat state, and then Z goes from the repeat state to the final state. And since it goes to a final state, it's in the language. But also, X, Y, Y, Z is in L. And actually, the way that we write this more compactly is X, Y with the power of 2Z is in L. So the 2 upstairs means 2 occurrences of Y. You can think of it like exponentiation, Y times Y. All right. But we can also see that if we choose any number I that we want, is in L for any choice of I that you want, because I could just go around that loop I times and get a whole new string out of it. One thing that we should note, though, is that the Y piece involves at least one transition, because it goes from the state to itself, eventually to itself. And since it's a DFA, there are no epsilon transitions. So that means that it must take at least one transition that it reads at least one character. But it could be one character. So we can note here that, actually I should note the first thing too, which is that X, Y to the I, Z is in L for all I at least 0. The second one is that the length of Y is at least 1. Equivalently, we can say that y is not equal to the empty string. That's just a consequence. And in fact, if we just stuck with those two, that's perfectly fine. But it turns out that there's a third condition that makes things significantly easier to prove. And the third condition is saying that the first two pieces, the x and the y part, just the x and the y part themselves. X and y together are at most the number of states in the DFA. And why is that the case? Well, there must be a repeat somewhere. But notably, if the string is really, 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 really long, there must be a repeat within the first p characters, no matter where it is. Because if we look at the first p characters and read just those p characters, we must see p plus 1 states. And so, in fact, we will see this exact same behavior among those first piece characters. So remember that the y piece is the part that repeats. So the end of y is either the pth character or before. So that means y completes within the first p characters. And since x occurs before the y part, it's tagged along for the ride also. So x and y together, the prefix of the string, is at most a number of states in the DFA. Cool. So we're actually able to prove, we actually already did prove, but I haven't stated it, the pumping lemma for regular languages, which strikes fear into the hearts of computer science undergrads the world over. But it's actually totally simple. The idea is we have to have a DFA in order for this to work. So that means the language that it's associated with has to be regular. So let L be a regular language. Then what we can do is, the way that this is phrased is that there's no DFA mentioned in the lemma statement, but it's referencing a DFA in the proof of it. So, and that actually comes out here. Oh yeah, another condition is at least the pumping length. I've already specified that up here. Yeah, that's not one of the three conditions that I'm thinking of, but it's a condition. You're right. Thanks, Albert. Okay, so let L be a regular language. Then there is a DFA for it, which has a certain number of states in it. So, yeah, then there exists a, what we call, it's just a term, it doesn't actually carry any weight, a pumping constant or length, sometimes used. I'm going to call P for this language L. Okay, so in the back of our minds, this P stands for the number of states in the DFA. Okay, that's what it represents. So then, in order for to get this looping behavior to actually work, we need to have strings that are accepted by the DFA, are in the language, and are long enough, which means have length at least P. And if you fail either one of those two properties, then we can't say anything about the other strings in the language. So for all W in L, so for all strings in the language, with the length of W being at least P, so the number of states in DFA, we've already seen that, then we need to break it up into that X and Y and Z thing. But it could be that there are many possible looping parts that it could be decomposed into. So all that matters is that there is a way to do so. So there exists X, Y, and Z such that W is equal to those three, because those are the three pieces, the beginning piece, the looping piece, and then the piece that goes to the final state. So W is equal to their concatenation, so that, and then we have those three conditions. So 1, x, y to the I, z is in L for all I at least 0. That's saying that we can go around the loop as many times as we want. The second one says that the length of y is at least 1, which is saying that it must involve at least one transition in the looping piece. And the third one, which is not required but is really, really useful, is that the first two pieces have at most p characters. At most the number of states in the DFA characters, but we labeled that as p. Okay, so that's actually it, and we've already proven this pumping lemma. So why is this even useful? So if the language is regular, then it must have these properties, because this is saying for any regular language you must have these properties. But if we find a language that does not have these properties, then it can't possibly be regular, because if it were, it would have the properties. So that tells us that we need to, for a certain language we want to show is not regular, we need to break something in here in order to show that it's not regular. So the way that it works is, let's actually look at this. This says for every choice of string that's long enough and in the language. So if I find one example that counteracts that for all, then we've proven that it doesn't have the right property, because the for all thing is broken if I find a string that breaks that. But then here, if we look at this, it says there exists a breakup of W into three pieces. So if I forget to show something goes wrong with some way of breaking it up, it could be that it could be broken up into those three pieces and everything carries through. So what I need to show is that every possible choice of breaking the string up into three pieces can't possibly work. So then if we look at all possible breakups like that, then it says here, for all I at least 0. If I find one choice of I such that it is not in the language anymore, that will give us a contradiction. Okay, and that's all we need. So let's prove, I'm sure all of you know this, the proof of this, but it's just so nice. So let's prove that this language right here, which is equal numbers of zeros and ones, is not regular. So is not regular. Okay, so how do we prove this? Well, in order to even apply the pumping lemma, we have to assume that the language is regular to start with. So let's suppose, and I got to give it a name, so I'm calling it L. So let's suppose that L is regular. I'm trying to prove that it isn't, which means I'm trying to get a contradiction eventually. So we know then, because of what the lemma says, that there exists this number P for L. So there exists the constant, the integer, the number P for L. Okay, which represents the number of states in the DFA. Okay, so now we gotta pick a string that's in the language and is length at least this number. And the obvious choice here is to choose W to be 0 to the P, 1 to the P. You could try to pick P over 2. The problem is that P might not be even, but there are ways to fix that. The thing is that by having the first P characters all be the same, then all the proofs of carry through really easily. Yeah, so in fact, all of the breakups into X, Y, Z are really, really, really easy now, because all the characters at the P characters at the beginning are the same. purely because of this third condition. That's why it's so useful. Okay, so then we got to look here at all possible breakups, so sad, of W into XYZ, according to the rules. So we know that X and Y are within the first P characters, which are all zeros. So that tells us that X is some number of zeros, and I'm going to call it A. So X has A zeros. It could be really any number, potentially, but it's some number of zeros. And then Y, let's call it B. And note that B has to be at least 1, because the length of Y has to be at least 1. So the number of characters in here has to be at least 1, which is what this is saying. And then Z, the way I do it, I just say, is the rest of the string, because there are only 3 pieces, and so Z has to incorporate the rest of the string. So let's see. What we need to do now is we're looking at all possible breakups according to the rules. And so what we can do is, let's try to find a choice of I, so that some number of copies of this Y string, so that we leave the language. And this is kind of an art, so you kind of have to get used to this, unfortunately. But let's pick I equal to 2. In fact, any value other than 1, because that's the original string, any value other than 1 will work in this case. So if we pick I equal to 2, then that's going to be X, Y, Y, Z, which is going to be, we're injecting 1 more copy of Y. So that means we're going to have an additional B characters into the string, zeros into the string. So when the dust settles, what we're going to have is P plus B, because we had P to start with over here. And we're going to have all of the ones that are untouched, because the Y part only has zeros in it at all. So we're going to have 1 to the P, no plus B on that one. So the thing to note is, this could still theoretically be in the language. So the only way this is in the language, the only way is if these 2 exponents are the same, because in order to be in this language, you have to have the same number of zeros and ones. So then is if the 2 exponents are the same, which means that P plus B is equal to P. But this is the same thing as saying that B is equal to 0, but that's a direct contradiction, because B is at least 1. So by finding that B is equal to 0, no matter what, that's a contradiction. And so there's no possible way that this this language could be regular, because if it did, then it would always stay in the language no matter which choice of I that we picked, but we found one that allowed us to exit the language. Cool. So feel free to put questions in the chat. I see that Manas put a really interesting one. So, okay. So I'm going to do a slightly different one than what you're doing, but the proof can be adapted pretty much exactly, which is the language of perfect squares. So I'm going to call it perf S, which is the set of all strings 0 to the n squared, where n is at least 0. Albert, context-free languages. Yep. Next stream on Sunday is going to have that, most assuredly. Okay, so this has this language has n squared number of zeros for every choice of n. So it has 0 zeros, 1 0, 4 zeros, 9 zeros, 16 zeros, etc. So I want to show that this is not regular. And I love this proof. It's so wonderful. Probably my favorite proof in the class, second favorite proof in the class. Okay, so what do we actually do here? Well, let's try to go through the same argument. So we need to suppose that this language, perf s, it really is regular. Then we know then that there exists that constant, a pumping constant, p for that language perf s. Okay, well, what can we actually do with this? Well, we gotta pick a string that is in the language and long enough being of length at least p. A really nice choice, and one that I recommend that you do, to choose w, the string w, to be a p squared number of zeros. And that's certainly in the language. And p squared is definitely bigger than p for all integers p. So therefore, this is in the language and long enough. The unfortunate thing sometimes is that some strings just don't work to get a contradiction, even if you pass both tests of being long enough and in the language. But this one will work. So the really interesting thing about this language, which is a unary language, meaning it has only one character in it, is that what am I trying to say? That we only really care about the lengths of the strings. I don't care about what the string is. I care about what the length of the string is. So here we see that the length of w is certainly equal to p squared, because that's what I defined it to be. So what we want to do, again, is to look at all decompositions. So we need to, again, look at all decompositions. If I miss one, then my proof is bunk. I need to look at every single one and show that none of them work. So most of the times, if we sub in p for the exponent in place of n, it works. Yes, that is very true. Sometimes you have like two different exponents that are slightly related to each other. So one of them might be p and the other one might be p plus 1. But yeah, it's usually a good idea to substitute n for p. Or substitute p for n, that's what I meant to say. So all decompositions, well, I don't care what the x, y, and the z parts are, but let's just say that the y piece is equal to b, the length of the length of the x piece is equal to a. And the z is obviously the rest of the string, and I can figure out what length that is. So what do we actually do with this? Well, let's try pumping up again, and this will work. So let's pump up. So pumping up means that we will choose a value of I bigger than 1, and pump down means we'll choose a value of I less than 1, which is the only one is 0. That's the only one you can pick. So if we pump up to I equal to 2, well, let's see what happens. Well, again, we only care about what the length of the string is. So the length of x, y, y, z is equal to, well, we're inserting b more characters into the string. So the length of the string, of course, is p squared plus b. It's hard to pronounce both of them in succession. Okay, so the only way this is in the language, perf s, is if p squared plus b is a perfect square. So that's the only possibility of it being in the language. Well, how can that possibly be? Well, the thing is, well, we know from everything that we've done. Oh, how'd you get p squared plus b? Well, we started off with p squared characters in. We can do this because they're all 0. All the characters are the same, so it doesn't matter. So we have p squared characters in. And I equal to 2 means that we're putting in an additional copy of y than what was already there. So we're putting b more characters in than what we had before. So p squared plus the amount that we added, which is b in this case. So that's how I get p squared plus b. Okay, well we know that b must be at least 1 because that's one of the conditions of the pumping lemma. So we know then from this that p squared is not equal to p squared plus b because this right-hand side is strictly bigger than this left side. So it can't be equal to this perfect square. In fact, we could do something even stronger and say p squared is strictly less than p squared plus b. So the thing is, this isn't enough to give a convincing proof because it could be that b itself is a big number because we're looking at a lot of decompositions. P doesn't change, but b across the different decompositions might change. So what we want to do is we want to show that it can't ever be a perfect square. So the great argument of this is the next perfect square is equal to p plus 1 whole thing squared, which is p squared plus 2p plus 1, if you remember your FOIL in arithmetic. Okay, so here's the big line. So p squared is strictly less than p squared plus b. We've already established that. And we know, but the thing is that b could be really anything. Here's the key. The key is that the length of xy is at most p, right? So this tells us that the length of y itself also is at most p, because the x string could be empty, but even if it had characters, why would it be even shorter? But y certainly can't itself be bigger than p, add at least something, and still get less than p. That's not possible. So the length of y itself is at most p. So this tells us right here that b itself is less than or equal to p. So what we get is that this is at most p squared plus p. And it could be equal, it might be equal. But look at these two numbers right here, these two. This one has a p, they both have a p squared in them. This one has 2p in it versus just 1. But the key is this plus 1 right here. This plus 1 will save us. So because it's plus 1, this thing is strictly more than this one. So this is strictly less than p squared plus 2p plus 1. And here's the magic. These two numbers right here are consecutive. Consecutive perfect squares. And so the length of the string that we got, which is this thing, I should write that too. So this is the length of the string x, y, y, z. And this number right here is the max possible length. Hold on. Max possible length of x, y, y, z. And what this tells us is that it's strictly contained between two consecutive perfect squares. So, and it's not equal to either one of them, which is a proof that it's not a perfect square. It can't be equal to a perfect square, not equal to two consecutive perfect squares and between them simultaneously. Isn't that amazing? I just love that argument. It's so clean and it's so slick in how it actually works. So this is a quick proof, I guess, to show that perfect squares are not regular, which is what I think Manas's question was earlier. You can adapt that argument to that language too. Okay, so that's all I really wanted to show for the first live stream today. So it was a long journey, but oh god, like 3.5 hours. But we actually went through everything in the regular language stuff. There are some things that I left out, but I think they are less important than the things that I covered, and I want a pretty short video here. So thank you all for watching. If you want to support the channel further, please like and subscribe to the channel. It really helps us out. There are many other links in the video description, such as donation if you want to do so. Please join the Discord server because I'm going to be posting these notes in there along with other things, potentially. And as always, I will see you all next time. The next live stream is on Sunday, so be there.